Greetings and welcome to Precalculus, Polynomials and Rational Functions. In this lesson, we're going to focus on the real zeros of the polynomial functions. Let's jump in here and talk about the real numbers, real zeros of a polynomial function. Now, we've already worked on this a little bit in previous lessons, but we're going to formalize this now. So, first of all, we have the definition. When we have a value and we place it and evaluate the function at that value and it equals 0, then that value is indeed a real zero. Now, the value that we have to plug in is a real number to be able to get a real zero out. Geometrically, it just means that it's the value where it crosses the x-axis, so it's an x-intercept. Algebraically, if we have some value like x minus c is a factor of f of x, that's what it means. So to be a real zero, it's where when you evaluate the function, you put in a real number, you get out 0. Or geometrically, it's an x-intercept. Or algebraically, where it is a solution to the function. So it's a factor of a function. X minus c, where c is your real number that you're plugging in. Now, the number of real zeros, if a polynomial has the degree of n, it has at most n real zeros. At most, not all of them have to be real zeros, but at most there will be n. So if you had a polynomial degree 3, it's going to have at most 3 real zeros. Why is this useful? Because generally we're searching for those real zeros. We're searching for the zeros of the function, and if our polynomial is degree 3, we know once we found 3 of them, we can stop, because at most it's going to have 3. Polynomials in factored form, if a polynomial in factored form, when we can solve each factor by 0 by using the zero factor property. These are things you've already done. It's just formalizing it now. We can also use the intermediate value theorem, where if we have a polynomial that cannot be factored, we can approximate the values of the real zeros, if any, by using the intermediate value theorem. And we've talked about that before. Again, this is nothing new. We're just formalizing all of it. So let's talk about the actual theorem, the real zero theorem. We are going to talk about several theorems in this lesson, and why they are useful is because when we look for real zeros, we got to know, 1, how many are we looking for? 2, when can we stop looking for them? Are there methods that we can use that will speed up the task? Are there methods that we can use to simplify the task? That's what these theorems will help us do. So let's say we have some function, a polynomial function, and it's in the form of a sub n x to the power of n plus a to the sub n minus 1 times x to the n minus 1, and so on and so forth, all the way down to a sub 1 x plus a sub 0, where just those sub values are just a way of indexing our coefficients. It's a polynomial with integer coefficients, and we want our first one and our last one not to be 0. Then we have this rational number, we're just going to call it p over q for right now, in lowest term, so it's a fraction in lowest term, that is a 0 of f. And here's the cool part about it. P is the factor of the constant that's at the end of the polynomial. It's the constant factor. And q is the factor of the leading coefficient of n. Now, it might not make sense right now, but just hang tight. We'll see several examples of it, and hopefully by the time that you see it a couple times, it will start making sense to you. Let's run through an entire example to using rational zeros theorem. So let's say we have this function, polynomial function f of x equals 2x cubed plus 5x squared minus 4x minus 3, where our leading coefficient is 2 and our last constant term is negative 3. So here's what we're going to do. We're going to list all possible rational zeros of f of x. Now it doesn't mean that they are the zeros of f of x. It's just the ones that we could check, or the ones that we would want to check. So here we go. It tells us the possible rational zeros, this is from our theorem, P over Q, the factors of negative 3, the last one, all over the factors of 2, which is the first leading term, the coefficient. Well, the factors of negative 3 are plus minus 1, plus minus 3. Now, here's the reason why it's plus minus 1, plus minus 3. Positive 1, negative 3 make a negative 3. Negative 1, positive 3 makes a negative 3. So I'm not going to write them out individually. If it is plus and minus, I'm just going to do both the plus and minus, positive and negative. Factors of 2 are positive and negative 1, positive, negative 2. Same reason. If I do positive 1 and positive 2, that makes a 2. If I do negative 1 times negative 2, that also gives me a positive 2. So these are all the factors. Now let's think about all the combinations using only the positive factors of the leading coefficient. So I don't care about this negative 1 and negative 2. I'm just going to use 1 and 2. Well, here we go. I could put the positive 1 with the positive 1 on top, well, the plus or minus 1. I could put the plus or minus 1 on top with the 2 on the bottom. Plus or minus 3 on top with the 1 on the bottom. And plus or minus 2 plus minus 3 with the 2 on the bottom. These are all the combinations where we have the constant, the factors of the constant term on top, and the factors of the leading coefficient on the bottom. Now let's reduce those fractions that we have. So negative positive 1 over 1 is just positive negative 1. Positive negative 1 over 2 is just positive negative 1/2. Positive negative 3 over 2 is positive negative 3/2. And positive negative 3 over 1 is just positive negative 3. These are all of the possible rational zeros of our function, which is kind of nice to know. We didn't do a lot of work to get there. Now we can use synthetic division to check which one of these are the factors we're looking for. Now let me just go right back up to our function. We are looking for 3, at most 3 real zeros. So here we go. Using synthetic division, I'm going to use 1 first, just positive 1. And sure enough, bring the 2 down. 1 times 2 is 2. 5 plus 2 is 7. 1 times 7 is 7. Negative 4 plus 7 is positive 3. 1 times positive 3 is 3. And negative 3 plus 3 is 0. And since we end with a 0, yes, 1 is a rational zero of our function. And in fact, x minus 1 is a factor. And this bottom line tells us when we factor x minus 1, what is remaining. So now our f of x can look like x minus 1 times 2x squared plus 7x plus 3. Now I just need to factor this, if it's possible, to find out what my other two factors are. So I'm going to take 2 times 3, I'm going to get a 6, I'm going to use my little snowflake method, and I end up getting that I can get 2 times 3 is 6, my middle term is 7. To get a 6, but to add to a 7, multiply to a 6 but add to a 7 is 6 and 1. So 2 over 6, because 2 is my leading coefficient, will reduce down to 1 over 3. 2 over 1 does not reduce, so my two new factors are 2x plus 1 from the 2 over 1, and 1 over 3 gives me x plus 3. Now I can solve those two factors I found using the zero factor property and find that my real zeros are -3, 1/2, and the 1 we used with our rational zeros theorem. Not bad, right? We didn't have to try and factor the whole thing. We didn't have to use long division. And we didn't have a term that we could use full on synthetic or long division until we found some possible values to be able to do that. Now, I can't stress enough, the rational zero theorem only identifies the possible rational zeros. It does not identify which, if any, any of them are actual zeros. We're going to have to take that step further and do like synthetic division to be able to test to see which of our possible ones are the actual zeros, if any of them are. So let's solve a polynomial equation, and we'll utilize what we know about the rational zero theorem. So here is our polynomial, 3x cubed minus 8x squared minus 8x plus 8 equals 0. We want to solve this. We know we're looking for at most 3 rational zeros. So here we go. Let's take the factors of the leading term and the constant term. So the factors of 3 are plus minus 1 and plus minus 3. The factors of 8 are plus minus 1, plus minus 2, plus minus 4, and plus minus 8. Now let's combine all of those with the possible values of our last term on top and our leading term on the bottom. And I'm only worried about the positive factors of the leading term. Now I'm going to have plus minus 1 over 1, plus minus 1 over 3, plus minus 2 over 1, plus minus 2 over 3, plus minus 4 over 1, plus minus 4 over 3, and plus minus 8 over 1, plus minus 8 over 3. So we have quite a few possible rational roots. We have 2, 4, 6, 8, 10, 12, 14, 16 possible roots. And what I'm going to do is strategically just start from this side and do positive 1, maybe have to do positive 2, maybe have to do positive 4, and I'm going to leave the fractions till last. But as soon as I find 1, let's say 2 is our actual root of our polynomial, then from there I'm down to a quadratic equation, and I can factor from there or use even the quadratic formula. I have a lot of tools to be able to solve a quadratic. I don't have a lot of tools to solve a cubic. So I'm just going to start with positive 1, and I'll keep going until I find something that works. There's really no rhyme or reason. You can select any of these to test, and I start with the positive values. All right, so when I test 1, I'm going to let you run through it yourself, the process. I just used synthetic division. 1 turned out to have a remainder of -5, and therefore 1 is not a 0. I grabbed 2 next, and I ran through the synthetic division, and I ended up with a -16 as a remainder. And so I know 2 is also not a 0 because I'm looking for a 0 at that last end. Now, I look at 1/3. Now I jumped around. I did decide to go to 1/3, and 1/3 turned out to be not a 0. And then I tried 2/3, and indeed 2/3 was a 0. Now again, I'll let you run through the synthetic division yourself. And there was really kind of no rhyme or reason as to why I picked those values. They just looked manageable to me. And now I know, since 2/3 is a factor, I know my polynomial of 3x cubed minus 8x squared minus 8x plus 8 will factor into x minus 2/3 times 3x squared minus 6x minus 12. That's my factor. Now I can try and factor this. Multiply 3 times negative 12. I could even factor out a 3, and I think that's what I did to try and make myself a little easier. So I factored out a 3 here. And this last factor turned out to be x squared minus 2x minus 4. Now I can track and factor this. So two values that multiply to negative 4 but add to a negative 2. I've got 4 and 1. They have to be opposite signs, so that's going to be a negative 3. Or I have 2 and 2, and when I subtract those, I get a 0. So there's no value that I can factor. So that, in terms of the easy stuff that I've tried, I'm going to go ahead and roll back to quadratic formula. So using quadratic formula, you know, that nice negative b plus or minus the square root of b squared minus 4ac all over 2a, I did use this method, and I ended up getting x equals 1 plus and minus the the plus and minus the square root of 5. So using my rational zero theorem, I found one of my answers was 2/3, and using the quadratic formula, I found my other two solutions were 1 plus the square root of 5 and 1 minus the square root of 5. So again, we had a third power degree polynomial, and I've got 3 real solutions. Now that doesn't always happen. I just want to put that out there. It's at most 3, and we found all 3, so we know we can stop. There's nothing else to do here. In our last example, we had a couple of irrational real values, real numbers as our solutions. We had 1 plus the square root of 5 and 1 minus the square root of 5. And it turns out we actually have a theorem to support that anytime I have one irrational value as my solution, I am going to have its conjugate. So, for example, 1 plus the square root of 5, its conjugate is 1 minus the square root of 5. So I changed the addition to the subtraction. Oh my gosh. I changed the addition to subtraction, and now it's its conjugate. And if it was originally subtraction, I change it to addition. So here's the formal theorem. It just means if I have a polynomial with integer coefficients and a plus b times the square root of c, where a, b, and c are real integers and c is greater than 0, it's an irrational 0 of p of x. Then a minus b times the square root of c is also an irrational 0 of p of x. So these conjugates come in pairs. All right. Another tool we have to find the zeros of the polynomial function. So that's that conjugate pair is a nice tool. And also this Descartes rule of signs. So here, let's say we have a function, and we'll call it, f of x, and it has real coefficients, and it's written in terms of descending order. Then the number of positive zeros of f is equal to the number of variations in the sign of f of x, or less than that number by an even integer. So I'm going to give you an example. Let's say we have a polynomial, and the variation of signs where it changes from adding to subtraction, or subtraction to addition, that happens 5 times. Then we know we have 5, or 5 minus 2 is 3, and 3 minus 2 is 1. So we have either 5 or 3 or 1 positive 0. Now the number of negative zeros is equal to the number of variations when we have f of negative x. And again, it's either that or less than that number by an even number. So let's say when we took f of x, we had 5 variations, but when we took f of negative x, that dropped down to 4 variations. Well, then we either have 4, or 4 minus 2 is 2, or 4 minus 2 is 0. So we have either 4, 2, or 0 negative zeros. It's just a nice tool that we have to be able to say, did we find all the positives? If we found all the positives, then we move on to the negatives. Now, the 0, a 0 of multiplicity m should be counted m times. So we do want to, once we find a solution, we do want to check it again. But once we've checked something below that value, we don't have to check it again. And we'll see an example of that. So let's see a variation of signs in example. 2x to the 5th minus 5x cubed plus 6x squared plus, minus 6x squared plus 7x plus 3. Now looking at where the signs are, the first sign is positive, then minus, then minus, then positive, then positive. We change from a positive to a negative, that's one variation. A negative to a positive, that's another variation. So this polynomial has 2 variations. So using the Descartes rule of sign, we either have 2 positive zeros of our polynomial, or we have 0 positive zeros of 0. Positive 0 of f's. Oh, I can't talk today. Let's try another one. X to the 5th minus 3x cubed plus 2x squared plus 5x minus 7. Now look at the signs. We have positive x to the 5th. So we count that as plus, minus, plus, plus, minus. So plus to minus is a variation. Minus to plus is a variation. Plus to plus is not, but plus to minus is. So in this case, we have 3 variations. So we do know we have either 3 positive integers, or 3 minus 2 is 1 positive integer. That's how we use this rule. Let's use our Descartes rule of signs to figure out the possible number of positive and negative zeros of our function f of x equals x to the 5th minus 3x cubed minus 5x squared plus 9x minus 7. First and foremost, we need to get the signs of our function. So we start off with a positive x to the 5th, then minus 3x squared cubed minus 5x squared plus 9x minus 7. So that's a plus, minus, minus, plus, minus. Looking at when it changes, the variation, it changes from positive to negative, then it stays negative, then negative to positive, and positive to negative. So we have 3 variations of signs. Knowing that we have 3 variations of signs, we know there must be, the number of positive zeros must be either 3 or 3 minus 2 is 1. So we can only have 3 or 1 positive zero. But we're not done yet. We want to see the number of negative zeros. That means we need to place a negative x into our function and see what happens. So when we place the negative x into our function, we get negative x to the 5th minus 3 negative x cubed minus 5 negative x squared plus 9 negative x times negative x minus 7. Now negative x to the 5th is going to be 5 negatives multiplied to each other, so that is still negative. Or I should say that is negative. Negative x cubed, again, that's an odd number, so that's going to come out negative. And a negative times a negative is a positive. Negative x squared, well, negative times negative is a positive, so that's going to be a negative 5x squared. And positive 9, but negative x is a negative 9x, and we don't have to worry about our constant term. So we end up getting a negative 5x to the 5th plus 3x cubed minus 5x squared minus 9x minus 7. So let's look at the signs. We've got negative, positive, negative, negative, negative. So in fact, we have one change from a negative to a positive. Then we have another change from a negative to a positive to a negative. So we have two variations. And therefore, the number of negative zeros must be either 2 or 2 minus 2 is 0. So we have 3 or 1 positive zeros, and we have 2 or 0 negative zeros. Now we do have some bounds on our real zeros, which is very helpful in terms of knowing how much further do we have to go before we can stop looking for zeros above a particular value and below a particular value. So we have this rule we get to play around with. If a polynomial has no zeros greater than some number, we're just going to call it k, then k is what's called an upper bound. And if our function has no zeros less than a particular number, again, we'll just call it k, then k is called a lower bound. We're going to be able to find this upper bound and lower bound. So remember when we had the example where we went all the way, possible zeros were plus minus 1, plus minus 2, plus minus 4, plus minus 8. If our upper bound was positive 4, then we wouldn't have to check 8 at all, because when we have a 0 that is not above 4, that means it can't be 8. Likewise, if our lower bound was negative 2, then I would not have to check any values less than negative 2. That's what's called bounds, and we're going to have a way of finding these bounds. All right, here are our rules for finding the bounds of our, like boundaries of our function. We're going to let our f of x be a polynomial function with real coefficients and a positive leading coefficient. Let's suppose f of x is synthetically divided by x minus k. Then, if k is greater than 0 and each number in the last row of the zeros is 0 or positive, then k is the upper bound on the zeros for f of x. If, for any k, the numbers in the last row alternate in signs, then k is the lower bound on the zeros of f of x. That is a really nice rule. So we know if k is positive and the last number, when we do the synthetic division on k, all of them are either zeros or positive, then k is your upper bound. And then for any k, in the last row, if it alternates in sign, then k is our lower bound. Zeros in the last row can be regarded as positive or negative, which helps with the alternating sign. So just consider zeros can be negative and positive. Let's run through an example. Let's find the upper and lower bounds on the zeros of f of x equals x to the fourth minus x cubed plus 5x squared minus x minus 6. Now, first and foremost, we need this rule. We know that all of these coefficients are real numbers, and we have a positive leading coefficient. So we can figure out these bounds by using our rules for our bounds. The possible rational zeros are going to be 1, plus minus 1, plus minus 2, plus minus 3, plus minus 6. Here's the reason why. My leading coefficient is 1. My last value is 6. Take all of the factors of 6, which are 1, 2, 3, 6, plus minus. And then our 1 here is plus minus 1. But plus minus 1 is down in the denominator, and I don't worry about the negative version of it. And therefore, I get plus minus 1, plus minus 2, plus minus 3, plus minus 6. By synthetic division, some value, x minus k, with k being our 1, 2, 3, 4, pop, pop, pop. So let's just try some of these possible rational zeros. I'm going to try the positives first. I'm going to try 1, 2, 3, 6, and if I have to do more, I'll do more. So with 1 and 2, let's see. Aha. So let's try 1. We get in our last row 1, 0, -5, -6, -12. These are not all positive, nor are oh my gosh, they're not all positive. We'll just stick with that. When we look at 2, we get 1, 1, -3, -7, -20. They're not all positive either. So I'm going to try 3 next. And it turns out 3, 1, 2, 1, 2, 0. And in fact, 3 is a 0 and it's our upper bound. And therefore, I don't have to check 6 to be a 0 because it won't be a 0. That row is all positive, and therefore that is my upper bound. And indeed, it is a 0. And the final step, which I've already kind of mentioned, is when we have our depressed equation is down to a quadratic. We can use any method we want, including the quadratic formula, to be able to solve this equation. All right, so let's run through it, all 7 steps. Finding the real zeros of a polynomial function. Let's say we have this polynomial, f of x equals 2x to the 5th minus x to the 4th minus 14x cubed plus 7x squared plus 24x minus 12. First things first, we want to do step 1, which is figure out what degree it is. Well, our degree is 5, so f of x has at most 5 real zeros. We don't have to go anything past 5 if we find 5. Second step, we want to look at the Descartes signs, rule of signs. So here we go. In front here is plus, so we have plus, minus, plus, plus, minus, minus, plus, plus, minus. Let's look at those variations. We have 3 variations, so we have the plus to the minus, then minus minus is the same, minus to plus, that's a variation. Plus to plus is not a variation, but plus to minus is a variation. So we have, now let's plug in the negative x and figure out what our variation is. When we plug in negative x, that's negative x to the 5th, so the positive becomes negative. Negative x to the 4th, well, that's positive, so that stays a negative from what it was before. Negative x cubed would be negative x cubed, so we have the negative goes to a positive. Negative x squared is positive, so positive times positive is a positive. Negative x times the positive is a negative, and then the 12 has no x, so it stays the same. So looking at this variation, we have negative, negative, positive, positive, negative, negative. We have 2 variations where we went from negative to positive and positive to negative. So what does this tell us? First of all, we have 3 variations, and therefore we have either 3 or 1 positive 0. And since we have 2 variations, we have either 2 or 0 negative. Now think about this. We're trying to get to possibly up to 5 real zeros. So it makes sense that here we're not going over 5, right? Step 3. Let's figure out, well, what are those possible rational zeros? We're going to take our 2 and our 12, and we're going to factor them. When we factor them, the factors of 12 are going to be 1, 2, 3, 4, 6, and 12, both the positives and the negatives. The factors of 2 are 1 and 2, both the positive and the negative, but we're really only going to be concerned with the positives down in the denominator. So when we group each of these up, make every single combination, we get 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1, and that's plus and minus, by the way. So that's just going to be plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. Then we have 1 over 2, 2 over 2, 3 over 2, 4 over 2, 6 over 2, and 12 over 2. That leaves us with plus or minus 1/2. Well, 2 over 2 is just 1. We already took care of that. Plus or minus 3/2. 4 over 2 was 2. We already took care of that. 6 over 2 is 3. We already took care of that. And 12 over 2 is 6. We already took care of that. So here are our possible zeros. Plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12, plus minus 1/2, plus minus 3/2. Step 3, done. Step 4, let's test for our zeros until we find a zero or an upper bound is found. So I'm going to concentrate on the positive whole numbers for now, because if we're finding an upper bound, we had 1/2 and 3/2. So if we test for a 2 and that turns out to be an upper bound, I actually don't need to test for 3, 4, 6, and 12. If 3 is our upper bound, then again, I don't need to test 4, 6, 12 for a 0 because we already found our upper bound. So I'll go ahead and start at 1 and stick with the whole numbers because they're easier to do. And let's figure this out. Okay, well, and if we have to, we'll do the fractions. All right, here's 1. We did not find a 0, nor did we find all the bottom row to be positive. If all the bottom row was positive, that is our upper bound. So not only did we not find a 0, this is not an upper bound as well. So 1 is not a 0 and it's not an upper bound. Let's try 2. 2 is a 0. So after we do the synthetic division, we do get a 0. But the bottom row is not all positive, and therefore it's not our upper bound. Okay, but it is a 0. So here's what we can do. Because we found a 0, we know that x minus 2 is a factor. So I'm going to go ahead and factor that out. And this bottom row tells us what our depressed function is. So x minus 2 times 2x to the 4th plus 3x cubed minus 8x squared minus 9x plus 6 is our new function we're going to be working on. Okay, taking this new function, pardon me, we have our new depressed function. I'm just going to call it q of 1 because we might have a lot of these depressed functions, so I'm just going to number them 1, 2, 3, 4, 5, 6. We get 2 x to the 4th plus 3x cubed minus 8x squared minus 9x plus 6. We're going to repeat step 3 and step 4 until we find our upper bound. All right, factors of this 6 are plus minus 1, plus minus 2, plus minus 3, plus minus 6. Factors of the 2, plus minus 1, plus minus 2. Therefore, our possible zeros could be 2, 3, 6. We're talking about the positive ones right now because we're still doing this idea of trying to find our upper bound. 2, 3, 6, 1/2, and 3/2. Now the reason why I crossed off the 1 is because 1 was not a 0 for the whole function, and therefore it's not going to be a solution for our depressed function. So we don't have to do 1. We do have to do 2 again because 2 could have had a multiplicity of more than 1. So we do want to continue to try 2 again. All right, let's look at 2. Doing the synthetic of 2, we do get all positives, but we do not get a 0. So 2 does not have the multiplicity more than 1. We know it only happens once. But our last row is all positive. So we know 2 is our upper bound. That means I don't have to test 3. I don't have to test 6. I don't have to test 4. I don't have to test 12. 2 is our upper bound. All right. Now, because it's our upper bound of our q, it is also our upper bound of our original function. Now, we get to skip this was kind of step 4, testing our zeros. Let's move on to step 5. Let's test the remaining positive entries that are less than 2. And we have 1/2 and 3/2. Using synthetic division on both the 1/2 and the 3/2, we get 1/2 using synthetic. I get a 0 for my remainder, so 1/2 is a 0. When I did 3/2, I did not get 0 for our remainder, so 3/2 is not a 0. Right? So we found 2 positive solutions, and using Descartes, I could have found 2 or I could have found 0, right? I'm just double checking. What was our value there? Okay, so let's move on. Now I know that our f of x can be written as x minus 2, x minus 1/2, and with our depressed function of 2x cubed plus 4x squared minus 6x minus 12, this is the new function we're going to be working on, right? Now, I'm going to go ahead and pull out the 2 that's in this last factor. So I pulled it out, but then I'm going to put it back in so I'm not working with 1/2. I don't want to, it doesn't matter that you're working with a fraction here, but I'm just going to put it back in just so it looks a little nicer and neater without the fraction. So I end up getting x minus 2 times 2x minus 1 times this new depressed function of x cubed plus 2x squared minus 3x minus 6. Here is our new depressed function, and I'm going to call it Q2. And guess what? We're going to repeat those steps again. I'm trying to get it down to a quadratic. So let's break down the factors of 6. We know those are 1, 2, 3, and 6, both positive and negatives. I have a 1 in front here, so that is negative and positive 1. I am not worried about the negative portion here, but here's the thing. Out of all my possible zeros, I have actually used up all my positives up to my upper boundary. So I am now going to test the negatives for the zeros, not the positives, because the only positives that I could have were, I'm trying to get that sheet. Yes. The only possible zeros I could have in positives were 1, 2, 3, 4, 6, 12, 1/2, and 3/2. We knew it wasn't anything over 2, so you could rule out those guys. And I've tested both 1, 2, 1/2, and 3/2. That only leaves the negative values. So I need to test the negative values. I don't need to test any more positive values. So I'm going to test 1, negative 1, negative 2, negative 3, negative 6 using my synthetic division. And it turns out negative 1, doing synthetic division, I get negative 2 as my remainder, therefore negative 1 is not a 0. But when I test negative 2, I get a 0, and therefore that is a 0 of our original function. Since it is a 0 of our depressed function, it is also a 0 of our original function. So let's go ahead and rewrite our original function using what we know so far. We now know that f of x is x minus 2 times 2x minus 1 times this x plus 2, because remember it's the opposite symbol, times x squared minus 3. We are down to a quadratic function, and therefore we can use any method that we want to solve this quadratic. Step 7. We finally made it to step 7. X squared minus 3 equals 0. I'm going to add 3 to both sides, and I get x squared equals 3. I'm going to take the square root of both sides, making sure I have plus or minus on the right-hand side. And I got x is plus or minus the square root of 3. We have now found all of the real zeros for our function. They are negative 2, negative 3, square root of 3, 1/2, square root of 3, and 2. And I just want to roll back to one thing that we talked about in the very beginning was the real zeros. Now we have 2 negatives and 3 positives. And lo and behold, our options were either 3 or 1 positive, 2 or 0 negatives. And indeed, we found 3 positives and 2 negatives for a total of 5 real zeros. So it's kind of cool that that really gives us a hint as to where we're going. And in fact, if I found all 3 real zeros with our first portion of this problem, I could stop. I wouldn't have to go on because I knew I could either have 3 or 1. That's all I could have. And I could move on to finding the negative ones. So that's the reason why that rule is kind of neat and cool. So we had at most 5 real zeros and we found all of them. So that problem complete. Now I do understand that these problems can be very lengthy, but hang in there. Once you get the process down, it goes a lot faster, and without too much overthinking, you can get through a problem fairly quickly. So it's just going to take a little bit of practice on your side to get a little bit faster with working through all of these steps. But once you get the steps down, it does go a little bit faster. So let's take an example of actually graphing our polynomial function. And finding all of the zeros are going to help out a lot in terms of graphing. Let's sketch the graph where f of x equals 3x cubed minus 2x squared minus 6x plus 4. Okay, here we go. Step 1, let's find all the zeros. So let's look at the degree. The degree is 3. It has a leading coefficient, the 3 is positive, and the end behavior is similar to x cubed. So that's a good thing to know, right? So when we sketch this graph, and if our end behavior doesn't look like an x cubed, which remember comes down and then curls kind of down. So it goes off to infinity on the left and down to negative infinity on the right. It should have that same end behavior. The middle part might be different, but the end behavior should be very similar to an x cubed. Second step, let's look at the variation of signs. So we have positive 3, negative 2, negative 6, positive 4. We have 2 sign changes there, variations of sign. Let's throw in a negative x and see what happens. Negative x cubed is a negative, so the positive times a negative is a negative. Negative x squared is a positive. Positive times negative is a negative. Negative x times negative is a positive, and the 4 doesn't have an x. So it looks like we have negative, negative, positive, positive. We have 1 variation of sign there. Now what does that mean? We will have either 2 or 0 positive zeros, and we will have 1 negative 0. Now, remember, it's degree 3. So if our degree is 3, we're looking for, at most, 3 real zeros. Let's go with the possible zeros. We're going to take this 3, factor it, 4, factor it. Remember, the 4 goes on top. So 4 can be factored in 1, 2, and 4, both plus and minus. The 3 can only be factored with 1 and 3. We're going to take all these combinations, thinking about just the positives on the denominator, and we get 1 over 1, 2 over 1, 4 over 1, 1 over 3, 2 over 3, 4 over 3, both plus and minuses for all of those. So here are our possible zeros. We have quite a few, but it's manageable. Now, let's start thinking about what possible zeros we have. I'm going to start with 1, 2, and go on. Okay, so 1. Once we do the synthetic division, I get a remainder of negative 1. And this is not a 0, and it is not an upper boundary, because if all of that was an upper boundary, all of these would be positive. Now let's look at 2. 2 is not a 0, but It is an upper boundary. So I could have stopped and said, okay, nothing past 2 is going to be a 0 because it is my upper boundary. But just to show you, you could do the 4. And again, you're saying, well, everything's positive because you already hit your upper boundary, and therefore 4 is not going to be any good. That was work I should not have had to do, knowing that that bottom row was all positive, knowing that 2 is an upper boundary. Although it is not 0, it's our upper boundary. So any zeros that are going to come are going to be less than 2 at this point. So because we know that, let's start testing our fractions. All of our fractions are less than 2. So let's go ahead and try 1/3 and 2/3, and we'll start there. All right, here we go. 1/3 is not a 0. 2/3 is a 0. So we found one of our positive zeros. And because we found one of our positive zeros, guess what? It is not 0 positive zeros. It's got to be 2 positive zeros. The only other positive value I have to check is 4/3. Let's go ahead and we could check 4/3, but once we get it down to 2/3 as our 0, this last row is actually quadratic. And so let's use a different technique to find the quadratic solutions. All right, let's rewrite our fraction with the 0 we know, which is 2/3. So x minus 2/3 times our last row, which was 3x squared plus 6. Well, I can factor out a 3 here to at least make my life a little bit easier. And I get 3 times x minus 2/3 times x squared minus 2. I'm going to go ahead and put the 3 back in there just so I don't have this fraction. It's easier to write without a fraction. You don't have to, but you get 3x minus 2 times x squared minus 2. Now we're going to, since it's quadratic, this x squared minus 2, we're going to go ahead and solve for x here. I'm going to say x squared minus 2 equals 0. Let's add 2 to both sides. We get x squared equals 2. Take the square root of both sides. We get x squared equals plus or minus the square root of 2. So here we go. Here are our zeros. We have 1 negative and 2 of them are positive. So negative square root of 2, 2/3, and square root of 2. So we know the zeros. These are x-intercepts. Now let's find the y-intercept. Since we know what the x-intercepts are, let's find the y-intercept. The y-intercept is when we plug in a 0 into the function and calculate what that is. So I'm going to go back to the original function, plug in a 0. And once we do that, we get zeros everywhere but a plus 4. And therefore our y-intercept is plus 4. Okay, that's another point that gives us a good idea about what this graph is going to look like. Next, let's throw in a negative x and see what happens here. So when I plug in a negative x cubed is negative, negative times positive is a negative. Negative x squared is positive, positive times the original negative is still negative. X is now negative x, negative times the original negative is a positive, and then we have our 4. Now, because here's what I'm trying to do. I'm trying to get symmetry. Does this graph have any symmetry? I know what my f of x is. My f of x and my f of negative x do not equal each other. And in fact, my f at negative x does not equal my negative function. So here's my negative function. Put a negative here, put a positive here, put a positive here, put a negative here. These two things would not equal one another, and therefore there's actually no symmetries. That's just a way of, hey, if I get half the graph graphed, I can just do a symmetry and graph the other half. So there are no symmetries to graph. Now we're going to test points for signs. Now you might be wondering, where are these steps coming from? In a previous lesson, we learned what steps we needed to take to graph a polynomial. So it's not the 7 we went through to find zeros. It's the steps that we are taking to graph a polynomial. Let's test some points for some signs. Well, we have this negative square root of 2, 2/3, and positive square root of 2. And I'm going to take points on either side of these and to test to see if our values are going to be negative and positive. So the values I'm just going to test are -2, right here, 0, 1, and 2. Could be any values between those. I just I tried to select values that were easy to calculate. Plugging a -2 in, I got a -16. Plugging a 0 in, we got the 4. Plugging a 1 in, I get a -1. And plugging a 2 into our original function, we get an 8. All right, so what's our sign of our graph? Well, our sign of our graph, it's going to be negative because we're -16, positive because we're +4, negative because we're -1, and positive because we're +8. That means this is below our x-axis, this is above our x-axis, below our x-axis, and above our x-axis. All right? So that gives us we've got some points that we can plot. We've got some idea about what our plot looks like in terms of where it's below and above. And therefore, we can do our final plotting. And once you do that, knowing that it has the appearance of an x cubed, which a generic x cubed would look like that type of thing, where you're going down, and I think I said it backwards before, I apologize, but you start up from -infinity on the left and then kind of make this squirrely mark and shoot off to +infinity. So I know the end of my graphs are going to look like that. The middle part is going to be helpful with what's going on with those points and the below and above axis. And once I graph it, here's what it looks like. I have the -2 down here, or negative square root of 2, negative square root of 2, positive square root of 2 is right here, and then the 2/3 is right here. So I have these 3 points, and I know my y-intercept. I know that from this region, which is the negative square root of 2, to the positive 2/3 is above the axis. I know to the left of -2 is below the axis. I know from 2/3 to positive square root of 2 is below the axis, and then it shoots off to infinity. Now, to be honest, I do not know if this really dips down or not. I would have to check some point in there. I do believe we have a 1 when we were testing, and for 1 we got a -1. So I do have this point right here as well. And therefore I know it didn't dip down all the way. If I didn't have this point, I wouldn't know, hey, where do I start swinging things back up? It still doesn't mean that I didn't swing down and then come back up. It's just this is the graph that I get. You can throw it into a graphing calculator and kind of see what's going on there. All right, so I have plugged into my graphing calculator the function 3x cubed minus 2x squared minus 6x plus 4. I've also manipulated my window just slightly. Let's see if I can get that focus so you can see a good shot of what it looks like on a calculator. And now I'm going to graph it. And there we go. That's my graph of my function. And in terms, I actually didn't do such a bad job sketching it. It does peak a little bit more up here before it comes back down, but I think I did a pretty good job sketching it, considering that using the points that we had. So that's it for this lecture. Until next time, be seeing you.